I kind of told you that this can get a little confusing because it's almost like we have 3 types of different problems all within part 3. So we are going to get to 2 types. So in case you're one of those that counts slides and looks for assignment slides and she's like, ugh, assignment slide, we're going to get to the second assignment slide, okay, which is, I think, 18 slides in. So we shall see, okay? That's kind of the deal. So for your homework, aren't these fun? I think they're kind of fun.
I like them. They're easy.
They are. And
they
so,
give me a headache.
well, that could be too. We're going to piggyback off of that, but the big difference that we're changing now is those were strong acids and strong bases, right? These are weak acids and weak bases, okay? So we have to handle them differently. So, of course, this isn't one of our 7 types of strong acids, okay? But here in a minute, it says it's a weak acid, okay? So, of course, we call that WA. When we talk about acids and base titrations, WA stands for weak acid. And so here in a minute, you're going to see the equilibrium where that thing, that HC6H4NO2 is going to kick off that first H, okay? So it's going to act as an acid, okay? But it's a 2-way arrow, right? So in this case, we're going to talk about that weak acid ionizing to a certain extent. So you're going to see an equilibrium arrow. They give you the molarity of the solution of the unionized species, and they give you the pH of the solution, okay? And they want you to find the Ka. And this is kind of similar to the regular Kc problems we worked before, where if you can knock out the equilibrium concentrations, you can plug them into the Kc expression and come up with a Kc. Same thing. We need to come up with the equilibrium concentrations of everything, plug them back into our Ka expression, and come out with a Ka. Okay. So yeah, just remember that this thing, if it's a weak acid, you got to use a 2-way arrow, not a 1-way arrow. And it's just like you guys did in your first homework set for this. Basically, you're going to show it kicking off a proton on the product side. So to work this problem, as a minimum, if you want to put a star there, you'd have to show that. And I'm going to kind of go through my notes, and then I'm going to break out and use an ICE diagram, the initial change and at equilibrium. Hi. So I'm going to break out and use an ice chart. You wouldn't have to use an ice chart, but I will. So yeah, so that's that. Okay, the Ka expression is like the Kc expression, where it's products raised to their stoichiometric coefficients divided by reactants raised to their stoichiometric coefficients. Okay, and I'll kind of give you a hint that basically. Well, no, I'm not going to give you that hint. I guess I can. You see this H plus? Okay. We know the H plus at equilibrium from the pH. Remember the pH was given? So basically, that is our equilibrium hydrogen ion concentration from our pH. Because remember, you can take what? 10 raised to the negative pH and get the hydrogen ion concentration. That's exactly what we're going to do. Okay. And to me, like I said, I think an ice table is going to be good for this one. Okay. So on the ice table here in a minute, I'm going to put, this is going to be my first row, the initial concentration. Here's one of the things you have to wrap your minds around. In acid-base chemistry, in this sort of problem, basically the initial concentration is the molarity of the weak acid. Some of it will ionize, and notice that the initial concentration of the H plus, zip. The initial concentration of what we're going to call the conjugate base, that C6H4NO2 negative, zip. Okay. So like I said, we're going to backtrack from the pH that was given to get our equilibrium concentration of our H plus. Okay, so we can do that because remember the pH was given. pH was 3.39, so 10 raised to the negative 3.39 is 4.1 times 10 to the minus 4th moles per liter. That is your hydrogen ion concentration at equilibrium. And remember, in the ICE tables, that is your third row, okay? So like I said, I'm going to pull up my ICE table here in a minute. Do that. I think I'll do it now. So here is putting those two things in. Okay, so this is the same problem. I'm kind of doodling it aside. Anytime they say they give you a weak acid like this, you're going to have to write the equilibrium. Trust me. Okay. Write the Ka expression, right? You can't write the Ka expression until you, to me, write your equilibrium. The initial concentration was 0.012 molar in the weak acid. Okay, initially you have, like I said, 0. And I have a slide here in a minute to say you're in just pure water. You might be saying, wait, Mrs. Snipes, because of autoionization in just pure water, your hydrogen ion concentration is 1.0 times 10 to the negative 7th molar, and you're right. But it's not enough to worry about. So here, for that same problem, is what I would do. Okay, here's my columns. I write the weak acid first, and then write the H plus, and then the C6H4NO2 negative. I get ready for my 3 rows, initial, change, and at equilibrium. And so filling in what we know, our initial is 0.012 molar, zip and zip. Okay, and then we did problems like this for just regular equilibrium constant expressions, where we know the molar concentration of one of the equilibrium species. In this case, it's the hydrogen ion. Okay, we got that from the pH, remember? And the stoichiometry is 1 across the board. So basically, we have a minus x, it's kind of in orange here. We have a minus x is going to happen to our weak acid. A plus x, of course, is going to happen to both our H plus and our conjugate base. Here in a minute, we're going to call those probably on Friday. Okay, so the orange is what's happening. Of course, we saw that we observed the change because of the pH of the hydrogen ion as a plus 4.1 times 10 negative 4th molar. That must also be the change of the C6H4NO2 negative plus 4.1 times 10 negative 4th molar. And then for the change in the weak acid, it's going to be a negative 4.1 times 10 negative 4th molar. So we take the initial, apply the change. Now here's the deal. The equilibrium concentrations, these are pretty obvious, right? Equilibrium concentration of the H plus and the conjugate base. So the equilibrium concentration of the weak acid, if in your calculators you take 0.012 minus 4.1 times 10 to the negative 4th, okay? But remember, since you're subtracting, you have to round according to 3 decimals. I'm going to do that too. We got time. 4.1 E negative 4. Yeah, I got point, for this number right here, my calculator displays 0.1159. So I have to round according to 3 decimals, and that's 0.0159 is what my calculator displays. So 3 decimals is 0.012. Okay? And actually, here in a minute, for us, the second type of problem, we're going to apply something called a simplifying assumption. And here's the deal. If you have indeed a pure weak acid, like this is, okay, the amount of weak acid that's going to, what we say, ionize or break apart is not much. So basically, you're going to end up with what you start with as far as the molarity of your weak acid. It's kind of a strange sort of thing, but it's the reality. So then I think in my notes all I say is we're going to plug those equilibrium concentrations back into the Ka expression. Okay, so in the numerator you have that 4.1 times 10 negative fourth could be squared if you wanted to. And the denominator, you have the molar concentration of the unionized, the weak acid itself, the 0.012. And rounding it to 2 sig figs, here in a minute you're going to see on my slides that the Ka, which is what we were supposed to knock out, the Ka for this weak acid is 1.4 times 10 to the negative fifth. It's like getting a Kc with one known equilibrium concentration, getting a Ka with one known equilibrium concentration. Right. So let's see what my slides say. So this is my little bit about, on our ice table, we put the molar concentration of the hydrogen ion initially is zilch, which actually for all intents and purposes, 1 times 10 to the negative 7th is insignificant compared to 4.1 times 10 to the negative 4th. All right. This is the same problem. Okay, just worked without an ice table. Let you guys kind of fill in what you need to there. I just like the ice charts. They're like, oh, I can clearly see what things are. But you really need to think of weak acids and weak base chemistry as just being like an extension of our equilibria we've been talking about. Oops, sorry, one last thing down here. Then just remember, like we did in the first column, the last row of the first column, we came up with the equilibrium concentration of the weak acid as essentially 0.012. Actually, that is what it is, rounded to 3 decimals. So if you don't use an ice table like I showed you, and I did push that out under Twitter before I came to class, then you need to explain, you need to show me what you're doing. Okay? All right. So this is just finishing up the problem like I did on my notes before. The goal of this was to knock out a Ka value, and we can get the Ka value by putting in equilibrium concentrations for everything. And there we have it.
So it'll just be easier to just make the ice chart and do it.
I think so, yeah. I like the ice chart. You figure you write your equilibrium, you write your Ka expression, you write your ice chart, and it's easier not to get confused, I think. So let's take a look at these right quick. These will be due on Friday. Trying something new. I'm like grouping my stuff. I think I like it. Nope, that's not it. That's the one we just did. There it is. So, there's always a catch, right? It's not really much of a catch, but that weak acid, the propionic acid, so it's got prop meaning 3, so it's got a carbon skeleton of 3 carbons. But anyway, they give you the moles of it and the volume. So you have to get the initial concentration, the molarity, using that ratio. So then it kind of looks like really similar to what we just did. But notice they don't give you pH, but they automatically give you the hydrogen ion concentration. Wasn't that nice of them? But remember that is actually the equilibrium molar concentration of the hydronium or the hydrogen ion concentration. Okay, to me that's almost an important part of working these. It says 65 mils of an aqueous solution containing that number of moles of propionic acid has a hydrogen ion concentration of blah. That's the equilibrium hydrogen ion concentration. Okay, so now your ice chart. Okay, so you write your equilibrium, your Ka expression, and your ice table, and fill in what you know. So the initial concentration of the propionic acid, the molarity, you're going to have to get from the moles in the volume. The initial concentration of the hydrogen ion or the hydronium ion is 0. 0 for the conjugate base. Okay, at equilibrium, okay, this molarity was given. That's that 0.00239, goes right there. That means that was the change. Notice we have a plus, same change here. We have a minus change here. Okay, why? Because basically it's going this way. So these are pluses, and that's minus. Stoichiometry is 1 across the board. If the stoichiometry had not been 1, we would have had to apply that. Okay, and then once you get those equilibrium concentrations, then plug into there, and that's it. Okay, so you were supposed to come up with a Ka for this one. The next one, it gives you the concentration of this weak acid in terms of grams per liter. So you're going to have to use your Chem 1 skills and get those grams into moles, right, using the molar mass. The formula is given. Notice that the hydrogen ion concentration was not given directly, but the pH was given, and so you can get to the hydrogen ion concentration. Okay, and I think that's kind of all the hints I have for that one. So equilibrium, what's missing here is the Ka expression. I probably wrote right the Ka. Oh, I did write the Ka expression. Okay, and in your ice table. All right. On to the second of the 2 that I'd like to cover today, or we need to cover today. So calculate the hydrogen ion concentration and the pH of this weak acid solution given this molarity and given the Ka value. Now this is like we did before, where you were given the Kc and you had to come up with equilibrium concentrations. Because basically on your ice table, that equilibrium concentration of your H+, okay, that's what you're after here. And once you get the molar concentration for H+, you can get your pH. You know, just take the negative log of it. Okay, so that's kind of what we're doing here. Okay, so I would start by writing the equilibrium. I don't know, I do not see how you could do this without writing the equilibrium. So it's a stated weak acid, so of course we're going to show it acting as an acid, kicking off a proton on the product side. And write your Ka expression. So if you're like me, you have to, just concentrate and make sure that you write it correctly, write your equilibrium correctly, and then from your equilibrium write your Ka expression correctly. In this case, the Ka value is given, and you're after the hydrogen ion concentration. So if you don't mind, I think I'm going to break out from this and show you kind of how I would do it with the ice table. And I did go ahead and push this out. This is available before I left my office again. So this is also available out there. All right. So this is what we got. There's your Ka expression at the top there in black. I have 3 columns on my ice chart. I have a column for my weak acid, CH3COOH. I have a column for my, for some reason I turned this around, I have a column for my conjugate base, which is the CH3COO negative. And then I have a column for my H+. We have initial change and at equilibrium. It's kind of like we ran into before. The initial concentration of the weak acid is the molarity that was given. The initial concentration of the things on your product side, including the H+ and that CH3COO negative, they're zilch, initial concentration. We weren't given any equilibrium concentrations. So in this case, notice we're going to have to go with the whole x thing, and the stoichiometry is a 1 to 1 to 1. You can see that in your Ka equilibrium. So we have minus x for our weak acid, and we have plus x for the other two things on the product side, for the CH3COO minus and for the H plus. So then our equilibrium concentrations look like this. At equilibrium, we take the initial weak acid, which was 0.10, apply the change, which was minus x. So at equilibrium, we have 0.10 minus x. At equilibrium, we have x quantities of the two things on the product side. So my little hint in red there is the whole crux of what we're supposed to do is come up with the hydrogen ion concentration, okay, which is x, and pH, which all we got to do is take negative log of that. But here's the catch for this sort of problem. Ooh, what is the catch? It is before plugging those values back into your Ka expression, what you need to do, because if you did, you'd come up with a quadratic. What you need to do is apply another simplifying assumption. And the simplifying assumption goes like this, and you need to state it. If x is sufficiently small relative to the initial concentration of your weak acid, which is 0.10, if x is much less than 0.10, that was the molarity of your weak acid, then that quantity, 0.10 minus x, essentially becomes 0.10. So you need to state that and apply it. So now if we plug these three equilibrium concentrations, this will be 0.10, x and x, back into your Ka expression. You won't end up with a quadratic. You'll end up with something very solved. You can very much solve for x. So your Ka would be equal to, that's not Ka squared, that's Ka is equal to x times x, that's your CH3COO minus and your H plus, divided by the molar concentration of your CH3COOH, which is 0.10, because we applied the simplifying assumption. And so that's all equal to the Ka that was given. Now this is where I'm going to leave this screen and go back to my notes. The point here is you can solve for x. Okay, you're just going to, it's not a quadratic sort of thing. Okay. And once we solve for x, we know the hydrogen ion concentration, and once we know the hydrogen ion concentration, we can get the pH, and that's how that goes. So that's how I would use an ice table. Okay, so back to my notes. This is kind of very much tracks like with the ice table. So at equilibrium, the molar concentration of your H plus and your CH3COO negative are both x. And at equilibrium, the molar concentration of your weak acid is that 0.10 minus x. That was our last row. And this is just the little caveat we ran into before. You know, is it fair to put zilch for the hydrogen ion concentration initially? And yeah, that's pretty. Yeah, that's it. Because of auto-ionization that we talked about before, water just automatically falls apart. It's not pure H2O molecules. Yep, that's pretty low. So here's the ice table. And this is the way we left it. Actually, almost the way we left it. This isn't the way we left it after we applied the simplifying assumption. I'll let you jot this down. This is without the simplifying assumption. And this I wouldn't leave it there. I would apply the simplifying assumption before I plug into the Ka expression, which is that. You don't want to have to use the quadratic. So instead of this, you're going to end up really with something like this. Oops, still not there. Okay, it's coming, it's coming, it's coming. This slide is an important one. You know, I said apply the simplifying assumption. That the point, that if X is sufficiently smaller, less than 0.10, which is the initial molar concentration of your weak acid, you know, you can assume then that molar concentration at equilibrium of your weak acid is 0.10. And this kind of puts a rule of thumb onto it. So it basically says if you take, the way you read this is if you take 100 times Ka, so if this is your Ka, 100 times Ka, I get 1.8 times 10 to the, what, negative third? Okay? And as long as the molar concentration of your weak acid is greater than that, you should be okay. So our weak acid is 0.10, okay? So that's your check. And 0.10 greater than 1.8 times 10 to the negative third, yeah. So it shows simplifying assumption should be okay. So finally, here's how we left it on the slide. X squared divided by 0.10 is equal to 1.8 times 10 to the negative fifth. And so I think I've talked about kind of flattening this thing out, kind of cross-multiplying across the equal sign. I'm going to take, on the next thing, I'm going to basically take x squared is equal to 1.8 times 10 to the negative fifth times 0.1, which is 1.8 times 10 to the negative sixth. Then to go ahead and get x by itself, take the square root of both sides. Okay, and when you do that, only 2 sig figs, okay, you get x is equal to 0.0013 moles per liter. And so if you look back at your ice chart, hopefully you'll be able to pick that out, and actually that's the molar concentration of the hydrogen ion. And that's what you're after. And the other thing we were supposed to knock out for this same solution is the pH. So like you did for your homework today, we're going to go ahead and do that. By the way, if you were to use the quadratic, actually the real solution is the same number. So to get from the pH, to get to the pH from the hydrogen ion concentration, we're going to take negative log base 10 of the hydrogen ion concentration. And then I'm going to hold you guys accountable to this because we've talked a lot about sig figs in this class. Of course, we have 2 significant figures there. In order to show 2 significant figures after you apply the log, that's 2 decimals on the other side. Well, that's it. Now we're on to the assignment slide. So take a look at these right quick. These will also be due on Friday. Looks like this. Okay. So what are the hydronium, hydrogen, right? Hydronium cation, hydrogen cation, and pH of a solution that is 0.143 molar. Now, you're supposed to memorize like 7 strong acids. If you're like me, this HNO2 throws me off. Strong acid. HNO3 is a strong acid, nitric acid, but HNO2 you're going to find on those weak acids, equilibria. So kind of true to form, my hint obviously is to write the equilibrium and then write the Ka and write an ice table. Okay. Initial change equilibrium. The initial concentration of the weak acids, 0.143 molar. Zip for the H plus, zip for the NO2 negative. Of course, the changes are going to be negative for the weak acid, plus X for the H plus X for the NO2 negative concentration. You see the equilibrium concentrations. Before you take those 3 equilibrium concentrations and plug them back into the Ka, I would, and you have to state your simplifying assumption, If you just use your simplifying assumption before stating it, you will not get full credit. So if x is significantly smaller, less than 0.143, then 0.143 minus x is essentially equal to 0.143. Then go ahead and plug those things back into your Ka expression. Notice in this one, the Ka for HNO2 was not given. You're going to have to look that up on the table. So that's 1 of 3. Solve for x. X is your hydrogen ion concentration, and then knock out pH from there. Your next one. Did I do this one? Oh. I didn't do anything for the next ones. My bad. I'll kind of doodle something here in a little bit and push it out there. But let's just look at it together. I don't have anything to show you per se. But again, it's a weak acid. You can see that hydrogen kicking off on the product side. I noticed a typo here, which there was a typo in another one. Either it's a typo or I truncated it. I don't know, you have to double check. There actually should be a negative sign there. Okay. So you're supposed to come up with not only the molar concentration of the hydrogen ion, but what's the molar concentration of this? Okay. Oh, there's 2 problems here, 2 ice tables. Okay, because they're giving you different molarities. In one case, it's 0.186 molar. In the other case, it's 0.121 molar. Okay, so 2 ice tables. Like I said, I'll kick something out there. But it probably won't be much other than you've already kind of seen. For 29, you're supposed to come up with, kind of like you did your homework, the hydrogen ion concentration or the hydronium cation, same thing, the hydroxide ion, the pH, and the pOH of this weak acid. So I guess my hint is going to start out something like this. You know, if somebody tells me this is a weak acid, I'm going to go ahead and knock out its, its equilibrium. Kicking off a proton, I would probably write its equilibrium constant expression, its Ka expression. And then I would write an ice table. And you're going to have to look up the Ka in order to finish this. And write an ice table, and I think you guys will do great. These are all very similar. The last one, oh yeah, I was supposed to look this up. So the last one, my hint is here, one of my hints, I guess. When it talks about the degree of ionization, actually A and B are related. The degree of ionization is basically the amount of the molarity of your, after it's kicked off a proton, so the molarity of your CH3, CH2, COO minus, that molarity divided by the molarity of your weak acid in the first place. I guess those would be equilibrium concentrations. CH3, CH2, CO2H, both at equilibrium. Okay, that is your degree of ionization. And then your percent is just your degree times 100. Sometimes students will get, they're like, what? Okay. So basically, in order to get these equilibrium concentrations, you're going to have to do what we've been doing, an ice table. That's the way I would do it anyway. Okay? All right, that's all I got. Study session after class.